All right, in this video, we're going to talk about section 3.3. This wraps up chapter 3 on describing, exploring, and comparing data. Here we're going to be looking at measures of relative standing in box plots. Now, already in 3.1, we talked about the measures of center. And in 3.2, we talked about the measure of variation. Now we're going to look at the measure of relative standing and box plots. Here we're going to develop the ability to compute a z-score and use the result to determine whether a given value of x is significantly low or significantly high. Also, we'll identify percentile values and quartile values from a set of data, and we'll develop the ability to construct a box plot from a set of data. Okay, so let's talk about some of the basics that are related to z-scores, percentiles, quartiles, and box plots. First, we'll talk about z-scores. All right, a z-score, or sometimes called a standardized value, is the number of standard deviations that a given value x is above or below the mean. Okay, so here we got two formulas here, one for the sample and the other one's for the population. More than likely, we're going to be using the one for the sample since we're dealing with sample data. And in this case, z is going to be equal to x minus x bar, all divided by s. X will be the given value, x bar is the sample mean, and s is the standard deviation. Okay. Now, if we were dealing with the population, we'll be using Greek letters here. Z is equal to x minus mu, which is your population mean, divided by sigma, which is your population standard deviation. Okay. Now, for the round-off rule, we always round the z-scores to 2 decimal places. Z-scores are always going to be to 2 decimal places. Okay. Now, we can use z-scores to identify significant values here. Okay. Significant values are going to be z-scores that are less than -2 or greater than +2. Okay. So here, for any z-value or z-score that is between -2 and 2, those values will not be significant. If you have a z-value less than or equal to -2, that's this area to the left of -2, including -2, that means your values are significantly low. Or if that z-value, of course, is greater than or equal to 2, that's in this direction, that means your z-values are significantly high. And I do want to mention that z-scores can be positive or negative. Okay. Z-scores can be positive or negative. So now let's look at some of the properties of z-scores. Number one is a z-score is a number of standard deviations that a given value x is above or below the mean. Number two, z-scores are expressed as numbers with no units of measurement. So z-scores have no units of measurement mentioned. Number three, a data value is significantly low if its z-score is less than or equal to -2, or significantly high if its z-score is greater than or equal to +2. And of course, if an individual value is less than the mean, its z-score is a negative number. Okay, so like I mentioned before, z-scores can be positive or it can be negative. So let's look at this first example that's related to z-scores here. It says here, researchers measured the data speeds for a particular smartphone carrier at 50 airports. The highest speed measured was 71.2 megabytes per second. The complete list of 50 data speeds has a mean of x bar equaling to 17.99 megabytes per second and a standard deviation of s equaling to 17.65 megabytes per second. So here we're going to answer parts A, B, C, and D. In part A, what is the difference between carrier's highest data speed and the mean of all 50 data speeds? Okay, so let's start with that. Finding the difference between the highest data speed, which was 71.2 megabytes per second. Now we're going to subtract from it the mean of all 50 data speeds, which is in this case 17.99. So if I subtract 17.99 from 71.2, I will end up with 53.21. So the difference between the carrier's highest data speed and the mean of all 50 data speeds is 53.21 megabytes per second. Now part B, how many standard deviations is that? And that's going to be the difference found in part A. All right, so we have to do there is just take that 53.21, which is the difference, divide that by the standard deviation of 17.65. Right now, in this case, put this out, 53.21 divided by 17.65. Now, we always round to two decimal places here, so it will be approximately 3.01. So here, the standard deviation, the number of standard deviations would be 3.01. And that means that the value of 71.2 is 3.01 standard deviations from the mean of 17.99. Now in part C is to convert the carrier's highest data speed to a z-score. Okay, now here you're going to see I'm going to use that z formula to come up with our z value. That's going to be equal to x minus x bar divided by s, which is what z is. Your x value in this case is at 71.2 minus your mean, which is 17.99 divided by the standard deviation of 17.65. So 71.2 minus 17.99, we found that out in part A, which is 53.21. And that's divided by 17.65. So if I do 53.2, well, I got that right here. Not necessarily needed to do that one. You'll see it's going to end up being 3.01. So that's actually your Z score for 71.2 megabytes per second. And now part D. If we consider data speeds that convert to a Z-score, that convert to Z-scores between -2 and 2 to be neither significantly low nor significantly high, is the carrier's highest data speed significant? In this case, it is, because 3.01 is actually bigger than +2. So that would fall. And if you look at this illustration right here, 3.01 would be to the right of 3. That would be in the area of being significantly high. So here, 71.2 megabytes per second would be considered to be significantly high. Okay. So that's how we answer example 1. All right, now example 2. Consider a value to be significantly low if its z-score less than or equal to -2, or consider a value to be significantly high if its z-score is greater than or equal to +2. A test is used to assess readiness for college in a recent year. The mean test score was 19.7 and the standard deviation was 5.1. Identify the test scores that are significantly low or significantly high. Well, we know what the mean is. The mean test score, that's going to be X bar, which is in this case 19.7. And the standard deviation, that's 5.1. That's given to us in the example. Okay. So now we want to find out the test scores that are significantly low or significantly high. Let's start off with significantly low. For something to be significantly low, the z-value has to be less than or equal to -2. So we're going to let z equal to -2 as the cutoff. And then use this formula, z is equal to x minus x bar, all divided by s. Now keep in mind here, we're trying to find out what x is. We already know what z is. We know what x bar is and what s is. So we're just going to substitute in this formula to find out what x is. That would be the significantly low value. Okay, so your z in this case is -2. That's equal to x minus x bar. That's 19.7 divided by 5.1. So here we have an algebra problem that we're going to have to solve for x. Well, that x minus 19.7, that's divided by 5.1. So that means the opposite of dividing will have to be to multiply. So what I'm going to do here is multiply both sides by 5.1. Okay. So this -2 will be multiplied by 5.1. Let's multiply by -2 here. And the x minus 19.7 divided by 5.1 will be multiplied by 5.1. So when I simplify this, 5.1 times -2 would be -10.2. That's equal to, now on the right side, the 5.1 in the numerator and the denominator divide out. So I'm going to have x minus 19.7. So here I'm going to solve this equation for x. X is being subtracted. We're subtracting 19.7 from x, so the opposite of that would be to add 19.7 to both sides. So that means x is equal to -10.2 plus 19.7 will end up being, I get 9 point. Okay, let's try this. -10.2 plus 19.7, that'd be 9.5. Okay, So any value that's less than 9.5, less than or equal to 9.5, would be significantly low. Now let's find the x value that would be significantly high. That would mean that z has to be equal to 2 or greater than 2. So here I'm still going to use this z equal to x minus x bar divided by s. But this time the z is going to be 2, and that's equal to x minus x bar, which is 19.7, divided by s, which is 5.1. Then I'm going to solve this equation the same way. I got the 5.1 in the denominator, so I need to multiply both sides of this equation by 5.1. So the 5.1 will be multiplied by 2, and the x minus 19.7 divided by 5.1. That's going to be multiplied by 5.1 as well. So here if I do 5.1 times 2, that's going to be 10.2. That's going to equal to x minus 19.7. And those 5.1s divide out. So here I have a simple equation. 10.2 is equal to x minus 19.7. So to solve for x, I add 19.7 on both sides. This of the x is equal to 10.2 plus 19.7 will be 29.9. So any x value that's bigger than 29.9 will be significantly high. And any x value that's less than 9.5, less than or equal to 9.5, would be significantly low. Okay, so in this case here, a test score is significantly low if its z-score is less than 9.5, or significantly high if its z-score is greater than or equal to 29.9. And I should say less than or equal to 9.5 or greater than or equal to 29.9. Okay, here's another example dealing with z-scores. That's this one. Based on sample data, newborn males have weights with a mean of 3,252.2 grams and a standard deviation of 543.9 grams. Newborn females have weights with a mean of 3,058.1 grams and a standard deviation of 751.3 grams. Who has the weight that is more extreme relative to the group from which they come from? A male who weighs 1,700 grams or a female who weighs 1,700 grams? Okay, so now let's look at males and females and calculate their z-scores to find out which one is more extreme. Starting with the males. Okay, we have a situation where the male who weighs 1,700 grams, that's our x value. And we're told newborn males have weights with a mean of 3,252.2 grams. So that's x bar. And the standard deviation of 543.9 grams. That's for men. So from here, I'm just going to calculate the z-score by doing z is equal to x minus x bar, whole things divided by s. The x value we're dealing with is 1,700 minus X bar, which is 3,252.2, all divided by the standard deviation, 543.9. Now, when I do 1,700 minus 3,252.2, I do this in the calculator. You'll see I get a negative value. So it'd be negative 1552.2. That will be divided by 543.9. So I'll go ahead and take that and divide that by the 543.9. Now we round the z values to 2 decimal places. So this will be a negative 2.85. Negative 2.85. So that's going to be the z value for a male who weighs 1,700 grams. And now for female. A female has the weight of 1,700 grams. That's given to us in that problem. But for females, newborn females have weights with a mean of 3,058.1 grams. So that's your X bar, 3,058.1 grams, and the standard deviation of 751.3 grams. And in this case, I want to find out what that z value is going to be for a female weighing 1,700 grams. So in this case here, I still use z is equal to x minus x bar divided by s. Your x is 1,700 minus x bar, 3,058.1. And that's divided by the standard deviation of 751.3. So if I do 1,700 minus 3,058.1, that'd be negative 1,358.1. Divide that by the 751.3. Okay, to 2 decimal places, this will end up being negative 1.81. Negative 1.81. I have to round the 2 decimal places here. Okay. So comparing those z values, pretty much we can see that the male who weighs 1,700 grams, that is more extreme relative to the group that in which he comes from. Okay. So the male weighing 1,700 grams will have a value that's more extreme than a female weighing 1,700 grams. Okay, so that's z values. Now let's talk about percentiles, which is another measure of relative standing. Percentiles are one type of quantiles or fractiles, which partition data into groups with roughly the same number of values in each group. So by definition, percentiles are going to be measures of location that's going to be denoted by P1, P2, all the way up to P 99. That divides the set into 100 groups with 1% of the values in each group. So let's think about this. P85 would represent the 85th percentile. That means on a standardized test, if you scored in the 85th percentile, that means you you perform better than 85% of the individuals that took that same test that you took. That's what we mean by percentiles. And the process of finding the percentile that corresponds to a particular data value, X, is given by the following. And we always round to the nearest whole number. And this is how we find the percentile of a value called X. That's going to be the number of values that are less than that X value divided by the total number of values. And then we multiply by 100. And then whatever we get, if we get a decimal, we always round up to the nearest whole number. Well, round to the nearest whole number. Doesn't necessarily mean you have to round up. It just says round to the nearest whole number. Like in this example, the following cell phone airport data speeds in megabytes per second are from a particular network. He'll want to find the percentile corresponding to the data speed of 9.8 megabytes per second. So let's find 9.8 in this data set. Here it is. Okay, the one I have circled is the .8. That's the data speed. We want to find out what that percentile is for that value. So to find the percentile for 9.8, the numerator is going to be the number of data values that are less than X. So here's 9.8. We need to count how many data values are less than 9.8. And as you can see here, there are 10, 20, 30, 40 values that are less than 9.8. So it'd be 40 divided by the total number of data values that we have in this set. It's going to be 10, 20, 30, 40, 50. Then that's going to be multiplied by 100. So in the calculator, you can do 40 divided by 50 times 100. And that would give us 80. And it's already a whole number, so we don't have to worry about rounding up or rounding to the nearest whole number. So that 80 means this, that the value of 9.8 is the 80th percentile. Okay, so we can say here that 9.8 megabytes per second corresponds to the 80th percentile. And what that means here is this, that 80% of the data speeds are less than 9.8. Okay. Now, next we're going to look at this. Well, let's talk about some notation. The n is the total number of values in the data set. Lowercase k would be the percentile being used for that data set. So for the 25th percentile, your k is going to be 25. Capital letter L is the locator that gives the position of the value. So for the 12th value of the sorted list, your L will be equal to 12. And P with the lowercase k, that's the k percentile. So P25 means the 25th percentile. Now what I have here is a flow chart that's going to show you how to convert the K percentile to a corresponding data value. And we have to use this right here. L is the locator. That's equal to K over 100 times N. Now that value only tells you the location of that data value, not the data value itself. It's just the location of it. So here's the flow chart. First of all, you want to sort the data from least to greatest, preferably. And then you're going to compute that L equal to K over 100 times N. K is the percentile in question, N is the number of data values. And then you're going to ask yourself this question. Is the L that you found out in that when you compute it, is L a whole number? If it is, then that means that the value of the K percentile is going to be midway between the Lth value and the next value in the sorted data set. So you're going to find piece of K by adding the Lth value and the next value and dividing that total number by 2. So let's say L was 11. That means it's a whole number. That means you have to look at the 11th number and the 12th number to find out what your percentile is. So you have to add, for example, the 11th and the 12th number together and divide by 2. And then if L was not a whole number, if it comes out to be a decimal, then you round up to the next larger whole number. And then the value of piece of K would be that Lth value. So if you came up with a decimal like L, let's say equals to 11.25, you round up to 12 and then look for the 12th number in that data set. Right. Now let's look at some examples of this. Well, let's look at one example of this. Here we want to use the following cell phone airport data speeds in megabytes per second from a particular network to find P90 or P sub 90. We're looking for the 90th percentile. And here's that data set. So if we're looking for the 90th percentile, that means K is going to be 90. And N is the number of data values in this set. In this case, it's 50. Okay, because each row has 10 numbers in it. So that's 10, 20, 30, 40, 50. Now let's find out what L is. And that's going to be K divided by 100 times N. Your K is 90, so that's going to be 90 over 100 times N, which is 50. And if you need to use your calculator, you can do that by doing 90 divided by 100 times 50. And that would give you 45. And notice we came up with a whole number. So L is 45. So to find the 90th percentile, we look at the 45th number in this data set and the 46th number in that data set. Take the average of the two. Okay. So it's that 45th number and the next number. And we take the average. So the 45th number, excuse me, of this data set, I know 10, 20, 30, 40, 41, 42, 43, 44, 45. The 12.6 is the 45th number. And then the 46th number is the number after that, 14.2. So we're going to take the average of those two. So 12.6 plus 14.2 will be 26.8. And 26.8 divided by 2 would be 13.4. Okay. So that means the number that's in the 90th percentile is 13.4. Okay, so that's how we find the percentile when we know when we get L being a whole number. We have to look at that, the digit in that position, and the next number after it. So if the 45th number is the 12.6 here, the number after that is 14.2. We look at those two, take the average of the two. Okay, next we'll look at quartiles. All right, just as there are 99 percentiles that divide the data into 100 groups, there are quartiles that divide the data into 4 groups. So here we have a description of quartiles. One of them is the first quartile, or Q1. And that is the same as the 25th percentile, which is P25. What it does is separates the bottom 25% of the sorted values from the top 75%. And then Q2 is the second quartile. And that's the same as the 50th percentile. Also, it's the same as the median. That's the middle number, if you recall, in section 3.1. What the second quartile does, or the median does, is separates the bottom 50% from the sorted values from the top 50%. Separates the top half from the bottom half. And then Q3, which is the third quartile, that would be the 75th percentile. What that does is separates the bottom 75% of the sorted values from the top 25%. So in this case here, here's an illustration of that. If we have our lowest value and our highest value, that's the minimum and the maximum, you can see the first quartile separates the bottom 25% from the top 75%. The second quartile, or the median, or the 50th percentile, separates the bottom half from the lower half. And then the third quartile, or the 75th percentile, what that does is separates the bottom 75% from the top 25%. Okay. Now, on the next page are other statistics that are defined using quartiles and percentiles as this. The interquartile range, abbreviated IQR, we take the difference between the third quartile and the first quartile. Then they have the semi-interquartile range. Here you do Q3 minus Q1. That's divided by 2. That difference will be divided by 2 to get the semi-interquartile range. And then the mid-quartile range is just you add the third quartile to the first quartile, divide that by 2. And then the 10 to 90 percentile range, we use the 90th percentile and the 10th percentile. We find the difference between those two. Okay. So now let's look at an example that is related to quartiles here. Like in this example, let's say I want to use the following cell phone airport data speeds in megabytes per second from a particular network to find the 25th percentile, or P25. So in this case here, we're finding the 25th percentile, so that means your K is going to be 25. And N, again, that's going to be 50. As each row has 10 of them, so there's 5 rows, so 5 times 10 must be 50. Now let's find the location using this formula. L is equal to K over 100 times N. So your K is going to be the 25 over 100 times N, or times 50. So on the calculator, if I do 25 divided by 100 times 50, I would get 12.5. Notice I came up with a decimal for my location, or for my locator. That means I need to round this up to the next whole number. So 12.5 rounds up to 13. Now, had that been 12.2, I still have to round up to the next whole number, which is 13 in this case. So that 13 represents the 13th number in that data set. So the 25th percentile is the 13th value. So I need to count to the 13th value here. So that first row, that's 10, 11, 12, 13. And the 13th number there is 0.6. So that means 0.6 represents the 25th percentile. Okay. All right, next we'll look at the 5-number summary and the box plot. Because the 5-number summary will help us construct a box plot. The values of the 3 quartiles are used for the 5-number summary and the construction of box plot graphs. Okay, so here's the definition of a 5-number summary. It consists of these 5 values. You will have the minimum, then the first quartile, which is Q1, then the second quartile, which is Q2, that's the same as the median, the third quartile, Q3, and then the maximum. So those 5 make up the 5-number summary. And you'll see an illustration of the box plot here. Now, a box plot or a box and whisker diagram is a graph of a data set that consists of a line extending from the minimum value to the maximum value, and a box with lines drawn at the first quartile, which is Q1, the median, and the third quartile, Q3. So that's what the box and whisker diagram looks like. Because notice at the minimum, you have a whisker drawn from the minimum point up to Q1, and then another whisker drawn from Q3 all the way out to the maximum. And this box represents those vertical bars here. The first one in the box is Q1, the one inside the box is your median, and the one that's on the end is Q3. All right, next is a procedure for constructing a box plot. And that's this. You first find the 5-number summary, which is the minimum value, Q1, Q2, Q3, and the maximum value. Number 2, construct a scale with the values that include the minimum and maximum data values. And then number 3, construct a box or a rectangle extending from Q1 to Q3. Draw a line inside the box at the value of Q2, which is your median, and then draw lines extending outward from the box to the minimum and maximum values. Okay, that's how we construct a box plot. And we're going to do that in example 7. Says here listed below are amounts of strontium-90 in a simple random sample of baby teeth obtained from residents in a region born after 1979. Use the given data to construct a box plot and identify the 5-number summary. Well, this first identify the 5-number summary that will help us create the box plot. Okay, so our 5-number summary consists of these 5 things: the minimum, and then Q1, then Q2, which is of course the median, so I'm going to call that the median instead of Q2. And then Q3, and then the maximum. Now, by looking at this data set, we can see that it is already sorted from least to greatest. It's already sorted from least to greatest. Now, we can easily identify the minimum. That's the smallest number, in this case, 129. I can also look at this data set and identify the maximum. Here's the maximum data value, 180. Here we're going to have to do a little work with the Q1, the median, and the Q3. Okay, so let's first find the median first. And that's, of course, the middle number. So in this case, the way I do this, just cross out the numbers on the left end and the right end and just keep crossing the numbers out on the end until I get to the middle number. So I'll cross out 129, 180, then 132, 174, 135, 171, 139, 171 here, 141, 168, 145, 165, 145 again, 162, 148, 159, 152, 158. Notice these are my 2 middle numbers, 154 and 158. So for the median, is going to be the average of the 2 middle numbers here, 158 and 154. That sum is divided by 2. So if I add 158 and 154 together, I will get 312. 312 divided by 2 will be 156. So the median of this data set is 156. Okay. Now we got to find Q1 and Q3. So let's start with Q1. Q1 is the same as the 25th percentile. So now we got to use L is equal to K over 100 times N. And K in this case is 25 divided by 100 times N. And in this case, N is 20. There are 20 data values in this set. So if I do 25 divided by 100 times 20, I'm going to end up with a whole number of 5. And L is a whole number, so I need to look at not only the 5th number, I need to look at the 6th number as well and get the average of the 2. So in this case here, Q1 is going to be the 5th plus the 6th number divided by 2. The 5th number in this case is, the 5th number is 141, and the 6th number is 145. So I got 141 plus 145 divided by 2. 141 plus 145 would be 286. 286 divided by 2 would be 143. So the first quartile is the number 143. And now I need to look for Q3. And that's the 75th percentile. Just say P75. So it's going to be L is equal to, K this time is 75 divided by 100 times N, which is still going to be 20. So if I do 75 divided by 20, 75 divided by 100 times 20, that would give me, I come up with 15. So now I came up with a whole number just like I did for Q1. So I got to look at the 15th and the 16th number. So Q3 is the 15th plus the 16th number divided by 2. The 15th number, that's the 10, 11, 12, 13, 14, 15. The 15th number is 165 plus the 16th number, 168 divided by 2. 165 plus 168 will be 333. 333 divided by 2 would be 166.5. So in this case here, Q3 is 166.5. So this is my 5-number summary. Now the next thing you need to do here is construct the box plot from this 5-number summary. Okay, so I'm going to draw a number line down here. Let's see. The smallest is 129, so I'm going to start at 120. I'm going to do these in increments of 10. So it's going to be 120 up to 130, then 140, 150, 160, 170, 180. And here we're going to have to kind of estimate where these values are on the scale. So in this case here, starting with 129, that's the minimum, that's close to 130. So I'm just going to draw a small line there. That's the minimum. Q1 is 143. Well, here's 140. I'm going to put 143 right here. But here I'm going to draw a longer line because that's going to represent the part of the box. And then 156, let's say 156 is about right here. So I'm going to draw a line that's equally the same as Q1, because that's part of the box. And then Q3 is 166.5, somewhere about right here. So let me go ahead and draw in this box, because this represents Q1, that's Q2, and that's Q3. And then your maximum is 180. Well, 180 is there. Now, this is where I draw the whiskers. That extends from the minimum value up to Q1. The other whisker will extend from Q3 up to the maximum value. Okay, so that's what our box and whisker plot looks like for this data set. And that's how we construct a box and whisker plot. Okay. All right, here's another example. As you might come across a situation like this one. 14 different second-year medical students at a hospital measured the blood pressure of the same person. The systolic readings are listed below. Use the given data to construct a box plot and identify the 5-number summary. Okay. Now, the first thing you see here are the 14 numbers. The problem with that is they are not in numerical order from least to greatest. So here you have to sort the data values first before you do anything. Okay, let's sort this data set. And I've already done it for you, so I'll just go ahead and write it out here. 120, and then 120 again. 121, 125, 128, 130, 135, 137, 140, 144, 146, 147, 150, and another 150. So if your data set is not in order from least to greatest, you need to sort that data set first and then do your 5-number summary. Okay, because in the 5-number summary, you need the minimum, and then Q1, and then the median. That's the same as Q2, and then Q3, and then your maximum. Well, we can find out what the minimum is. The minimum there is 120, the smallest number in that data set. The maximum is the largest number. We see that's 150. Now we need to find the median of this data set. So let's do this. Using this sorted data set, not the original data set that's not sorted, it has to be sorted before you can find the median. Okay. I'm going to do this. I'm going to underline the number on the left and on the right and keep doing that until I get to the middle number like this. Probably easier to do it that way. Here are my 2 middle numbers, 135 and 137. So the median is this, the sum of those 2 middle numbers divided by 2. 135 and 137 divided by 2. Here I'm taking the average of the 2 middle numbers to get that median. 135 and 137 is 272. 272 divided by 2 would be 136. So the median is 136. Now let's find Q1. And that's going to be the 25th percentile. And to do that, we have to use L is equal to K over 100 divided by times N. K over 100 times N. So this time K is 25 divided by 100 times, and there are 14 data sets. Data values here. So 25 divided by 100, then you multiply by 14, you're going to get a decimal of 3.5. So when we get a decimal for our L, we need to round up to the next larger number. That would be 4. So we need to identify the 4th number in that data set. Now we have to look at the sorted data set. So the 4th number there would be 125. So the 25th percentile is the number 125. Or we can just say Q1. And now for Q3. All right, Q3 is the 75th percentile. So to find L, that's still going to be K over 100 times N. But here K is 75 divided by 100 times 14. Now, if you take 75 divided by 100, multiply it by 14, you'll get, as a decimal, 10.5. Now here, we need to round this up to 11. So we're looking for the 11th number in this data set. So here, if I count using that sorted data set, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's the number 146. So Q3 would be 146. So here I have my 5-number summary. All right, now next we'll go ahead and construct that box plot for that 5-number summary. So we start with 120 since that's the minimum, and then in increments of 10, this would be 130, 140, 150, and I'll stop at 150 because that's the maximum. All right, so 120 is your minimum. So I'm going to draw a small vertical bar at 120. And at 125, which is halfway between 120 and 130, I'm going to draw a larger bar for that. That's part of the box. The median is 136. Let's see. I'll put it about right here. Draw that bar that's equal to the one for the Q1. 146 is Q3. It's about right here. These three represent the box. So I'm going to draw in the box. And then 150 is your maximum. Here's 150. Draw a smaller bar. So now the whisker on the left connects from the minimum to Q1. The whisker on the right represents the part from Q3 up to the maximum. So that right there represents your box and whisker plot for this data set. Okay. All right, and finally, we'll kind of talk about outliers and modified box plots. An outlier is a value that lies very far away from the vast majority of the other values in the data set. For constructing modified box plots, we can consider outliers to be data values meeting specific criteria based on quartiles and the interquartile range. All right, the first thing you're going to do is find Q1, Q2, and Q3. Those are your 3 quartiles. Next, you're going to find the interquartile range, which is going to be IQR equaling to the 3rd quartile, Q3, minus the 1st quartile, Q1. Then number 3 is evaluate 1.5 times that interquartile range. And it says here, in a modified box plot, the data value is an outlier if it is above Q3 by an amount greater than 1.5 times the interquartile range, or below Q1 by an amount greater than 1.5 times the interquartile range. Okay. And from that, we can construct a modified box plot. The box plots described earlier are called skeletal or regular box plots. A modified box plot is a regular box plot constructed with these modifications. One of them would be a special symbol such as an asterisk or point is used to identify outliers. And 2, the solid horizontal line extends only as far as the minimum data value that is not an outlier and the maximum data value that is not an outlier. Now, if you look on the next page, you'll see an example of a modified box plot for pulse rates. You can see these 2 dots here on the far end. Those are considered to be outliers. Okay, so let's construct a modified box plot for this data set. So here's our data set right here. It's already sorted from least to greatest. So we don't have to worry about trying to sort the data like we did in the last example. Okay, so now my 5-number summary. Then Q1, and then the median, then Q3, and then maximum. Okay, so the first thing we're going to do is find out what Q1, Q2, and Q3 are. Q1 is, of course, the first quartile. Q2 is the median. Q3 is the third quartile. Let's start off with Q1, which is, of course, the 25th percentile. The location of that would be K, which is 25, divided by 100 times. Let's count how many data values we have here. 12. So it'd be 25 divided by 100 times 12. Now, if you were to do that in the calculator, you'll get L is equal to 3, which is a whole number. So that means not only do we look at the third number, we have to also look at the fourth number and get the average of the two. Okay, so the 25th percentile, that would be the third and the fourth number divided by 2. The third number in this case is 44. The fourth number in this case is 56. And that's divided by 2. So 44 plus 56 is 100. 100 divided by 2 would be 50. So that 50 represents the first quartile. And then the median. Let's see. I just underline the numbers on the far left and on the far right until I get to the middle number, like this. Well, notice I got two middle numbers, 82 and 115. So I need to get the average of the two middle numbers here. So here, if I do 82 plus 115, divide that by 2, well, 82 plus 115 is 197. 197 divided by 2 will be 98.5. That would be your median, 98.5. And then Q3. That's, of course, the 75th percentile. So here L is going to be equal to 25. No, not 25, 75. Because we're looking for the 75th percentile. So 75 divided by 100 times N. And N is 12. So if I do 75 divided by 100 and then multiply by 12, I would get 9. And it came out to be a whole number. So I need to look at not only the 9th number, I need to look at the 10th number. Okay. So Q3 is the 9th plus the 10th number in that data set divided by 2. So if I look for the 9th number, that's 3, 4, 5, 6, 7, 8, 9, that's 125. And the next number, which is the 10th number, that's 133 divided by 2. Let's see, 125 divided by, 125 plus 133 is 258. 258 divided by 2 is 129. So that's Q3, 129. Okay. Now I've yet to find the minimum and the maximum number. because I have to find out whether or not I have outliers in this data set. And I need to identify what they are. Okay. To do that, let's find what they call the interquartile range, or IQR. That's, of course, is Q3 minus Q1. The Q1, well, Q3 is 129 minus Q1 is 50. So 129 minus 50 will be 79. So the interquartile range will be 79. Okay. So let's find out what our outlier is going to be, if there are any. So I got to do Q3 plus 1.5 times the interquartile range. And whatever I get for that, if one of these data values is greater than that interquartile, greater than that amount, then that data value is an outlier. Let's see, Q3 was 129 plus 1.5 times the interquartile range is 79. So we're going to do 129 plus 1.5 times 79. I get 247.5. Now, if I have a data value that's bigger than 247.5, then that data value will be the outlier. If I look in this data set, notice that 360 is bigger than 247.5. So that means one of my outliers is 360. And I also got to do Q1 minus 1.5 times that interquartile range. And if I have a data value that's less than the value that I get for this, then that means that data value is also an outlier. Let's see, Q1 was 50 minus 1.5 times the interquartile range was 79. So 50 minus 1.5 times 79, yeah, I'm going to get negative 68.5. And if you look at that data set, there are no values that are less than negative 68.5. So on the left side, I don't have any outliers there. But on the right side, 360 is the only outlier for this data set. So the outlier is 360. And if my outlier is 360, that means 240 will have to be the maximum for this data set. I have to use 240 as the maximum because the 360 is the outlier in this modified box plot. Now, if I was just doing a regular box plot, then 360 would be the maximum. Okay, so now let's use our minimum. We can find out what that minimum is. That's 21 because I don't have any outliers on the left-hand side. So 21 is your minimum. So there's my 5-number summary. I can construct a box plot. And yes, this is going to take a lot of space because of the data values that I have here, unfortunately. So I'm going to start at 0, then 20, let's see, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 40, 60, 80, 300, 320, 40, stop at 360. Okay. And I'll fill in the rest. Okay. So now, the minimum is 21, which is a little bit past 20. I'm going to say it's about right here, and I'm going to draw a small line there. Q1 was 50, halfway between 40 and 60. So I'm going to draw a larger line, longer line there. The median was 98.5. Okay. I just might need to zoom out a bit so that you can see this. Okay. Q3 is 129. I'm going to say about right here. So those three longer lines represent the box. The maximum is 240. So here's 240 way out here. Now for the outlier 360, that's way over here. So I'm going to draw a dot there to represent that data value is an outlier. Sometimes an asterisk can be used as well. And now I'm going to draw my whiskers from the minimum to Q1, and the other one from Q3 all the way out to the maximum. So this is what a modified box plot looks like for this data set. Okay. Okay. So that does wrap up this section on measures of relative standing and box plot. I wish you the best on the homework assignment for this particular section, and do feel free to email me if you have any questions about any of the problems in the homework.